let's get started again. So there is homework for you, boo. There's homework for you in the folder, okay? Maybe later today, after you've had some time to work on it, I will also post the solutions to that homework. But in order to complete your homework, you have to do the origami, okay? That's part of the homework. You have to do the origami and you have to work in teams for problem number 3 with your origami, okay? So that's part of that, okay?
Are you grading it?
No, you will not be turning it in. I will never know, okay, if you don't do it. But you're here for a reason, right? I don't think that your reason for being here is to slack off, or you wouldn't be in the room right now. You'd be in your hotel room, so try it out. Okay, so let's continue. We met our quantum algorithm here. And to be just a little bit more precise about what's going on, when we start the system here, we're starting it in a product state. So a non-entangled state, right? When we measure the output here, we do this digitization step. The actual output may be a big superposition state, and then we get only a single result from that superposition state in the ideal case. However, for a lot of quantum algorithms, what they do is they very cleverly use interference during the algorithm to ensure that the final state is an eigenstate of the measurement, okay? So for instance, Shor's algorithm, which you may have heard of, right, for factoring numbers, at the end of it, you basically should be getting one of the prime factors, okay? So this is kind of, the design of quantum algorithms is a black art as far as I'm concerned. The people who can do this really well are really remarkable. They've got some intuition that I struggle to gain myself, but they're very good at it. Okay. Circuit diagrams. So I told you that my goal here was to get you guys to the point where you know what these look like and what they mean. And so we're going to start using those now. So for a single qubit circuit, I'm going to have basically a single horizontal line, okay? This is what a quantum circuit for a single qubit might look like. And time flows from left to right in these, okay? So we start off with our qubit in some initial state, and this qubit is going to continue on this line. Basically, everywhere there's a single line there. Just means the qubit is evolving in time. 1 qubit gates are going to be boxes that only kind of intersect that one line. And usually we'll write something in the box, okay? It'll be the symbol for the operation. Like it might be X or S or T, okay, for X, S, or T gates, all right? And then this thing is a measurement, okay? And that's supposed to be a little galvanometer needle, like the old-timey displays on things. And in this particular diagram, I actually have the output of the measurement is being carried on some classical, say a wire or something, okay? All that means is that we have some classical information about the output, the outcome of that measurement. Okay. So we'll start with the initial state. For gate-based quantum computing, we usually start with a Z eigenstate, okay? So typically 0 or 1, perhaps even more to the point, almost always just zeros, okay? And conceptually, you can think of how are we going to do this? How can we take some physical system and do this? Well, if I have the ingredients that I've described to you, one of the things we could do is measure it in the Z basis. So we will get either a 1 or a 0, probabilistic, right? We can assign probabilities to those, but beyond the probabilities, we don't know the outcome. We'll get an actual outcome. It'll be in, for instance, the 1 state. So now this wire represents that qubit in the 1 state, and this classical wire carries the information to this, which will be a rotation that we can do, dependent upon the result of the classical wire, what's in the classical wire. So depending upon the output of our measurement, which actual measurement result we got, we either need to rotate it or not rotate it to create 0. So state preparation and state measurement are kind of the same thing here. In both cases, you might say I have some ignorance about the state of the system. Maybe it's classical ignorance. Maybe it's truly quantum mechanical, lack of determination. And then, at the end of it, you gain information about it, okay? For single qubit gates, we've already talked about the various rotations and how to represent those on the block sphere. And so an x rotation by pi is just a square with an x in it, okay? Y and z are the same thing. We also met the Hadamard right? Which was a pi rotation about an axis that is 45 degrees between the plus x and plus z axes, right? We had some rotations by smaller values, the s and t gates here. A general rotation is going to be drawn like this in a circuit diagram, where we have n hat is the direction of the rotation in the Bloch sphere space, and alpha is the amount of rotation we do. The measurement is the digitization step, where we get either a 1 or a 0. Okay? In fact, it's probably best to always say you measure in the z basis, and if you want to do a measurement in the x basis, what you would do is rotate it first, rotate the x information onto the z basis, then measure in the z basis and interpret it accordingly. Okay? And we call this 1 or 0, but remember, for a measurement operator, we get to assign the eigenvalues whatever we want. Okay? I gave the example where one of them was 7, the other one was minus 44. You could call one of them smiley face if you want. Okay? It's just some information. Okay? Now, there are two types of measurement that are, their difference is not important as a theorist, but as an experimentalist, it's very important. This is what we would call a destructive measurement, where we gain the classical information about the state of the qubit, but the qubit itself is either discarded or is in some state that we don't know what it is, right? Because the measurement process tends to be pretty invasive, okay? So the way that we do measurements in real quantum systems is not this ideal projective quantum measurement typically. We actually work very hard to do ideal projective quantum measurements. This is the more usual case. Typical case is that after the measurement, we would, if we want to reuse the qubit, we would then need to reinitialize it, okay? A true kind of ideal projective quantum measurement, sometimes is called quantum non-demolition, means that the qubit is left in the measured eigenstate, okay? Now we can create something like this, a situation that looks qualitatively like that, if we take this destructive one and then we initialize a qubit again, and provide its output there. But this is why there are going to be kind of two different types of diagrams associated with measurement, okay? So frequently it'll just turn into classical information, but if we want to keep the quantum information, you would have another line popping out there. Okay, so we're going to do an example circuit, and this is going to exhibit something called Rabi flopping. Okay, so we are going to have a single qubit. We'll initialize it on the south pole. Right, it's going to be in the 1 state. We're then going to perform a rotation about the y-axis of the Bloch sphere through some angle alpha. Then we're going to measure it in the z basis and see what we get. Okay, so remember rotations, right? We rotate the Bloch vector about the positive y-axis through some angle alpha. Okay, the actual time evolution operator or the operator associated with that operation looks like this. So if we start in the 1 state, we end up with this superposition of 1 and 0, and it comes up here like this. I think I'm missing. Might be missing an I there. Okay. Have to think about it. Okay. So we rotate, and then we're going to measure. All right. What are we going to get? Well, we can look at the probabilities. The probability that we measure 0 is going to be the overlap integral between 0 and the state that we're in, squared, right? Mod squared. And we can create the state that we're in. Remember, we started in 1, and then we have some time evolution operator, some propagator here associated with that. And it's going to be sine squared of alpha over 2. And if we do this for various values of the rotation angle, so what we're going to do is take our system, initialize it on the south pole of the Bloch sphere, rotate it through some angle alpha, measure it. I'm then going to take it again, initialize it, rotate it by some other slightly larger angle, alpha, measure it. Do it again and again and again. What are we going to get? You're going to get noise. The reason is that we're doing a single shot. The measurement outcome is either 0 or 1 here, no matter what, okay? So the way to learn more about what the quantum state is in this case is to do repeated measurements at each value of alpha. So we're going to initialize it, rotate, measure, initialize it, same rotation, measure, initialize it, same rotation, measure. Do that a bunch of times. We're going to average the results. And as we average down more and more shots per point, we start to see that we get this nice sinusoidal variation here, okay? And by the time we're at 5,000 shots per point, it looks pretty indistinguishable from a perfectly sampled sine curve, okay? So this used to bother me so much when I was a student. My quantum mechanics class told me that when you measure, you get 0 or 1. And then I would go to a talk and they would show data where this thing is all analog and I was like, what the heck is going on? And the answer is secretly there are repeated measurements in here, okay? Each time you definitely get 0 or you definitely get 1 at every single time. And what we do is we actually average those results together, okay? All right. There's another commonly encountered scenario. This is more common in quantum sensing than quantum computing. It's called Ramsey spectroscopy or Ramsey sensing. Some quantum algorithms have a bit of a flavor of this as well. But the circuit for this is as follows. We're going to start in the 1 state. We're going to do a Hadamard, rotation around the z-axis by alpha, and another Hadamard, and then measure. Okay? Now, if you remember what a Hadamard does, it's going to take the 1 state and put it up on the equator of the Bloch sphere. So we start off at the South Pole. We're going to go up to the equator. We then have a rotation about the z-axis, right, through some angle. And then this other Hadamard is going to map back from the equator back onto the North and South Pole. And then we're going to measure here. Okay? And so this is our evolution operator. You can write it out kind of in long form like that. And what we get here again is that we have a similar sort of thing for the probability. And of course, we would do this many times. And when we average the results, this is what we get. Okay? So this blue curve is really just sine squared of alpha over 2. And so in quantum sensing, this z rotation is actually your signal. You don't intentionally do a z rotation of whatever your qubit is. What you do is the thing you're trying to measure causes that z rotation. For instance, a magnetic field. Okay, and that's how you get that information. Okay. Now it's time for 2-qubit gates. I didn't do my animation quite right here, but a classical 2-bit gates, okay, well, we can map their behavior onto Boolean logic, onto kind of true-false, right? So if you've ever taken a class in like symbolic logic or anything like that, we have our inputs, A and B, and then this is a NAND gate. This is like not A and B, okay? And this is a universal gate for, as you may know, for classical computation here. We can basically generate any arbitrary circuit using just those, okay? This is not reversible, you may have noticed, okay? So I started with 2 wires and I end up with 1 wire, right? So if I tell you what the result of not A and B is, you don't necessarily know what A and what B were before then, right? You've lost information here. We don't really have that in quantum mechanics, right? Quantum mechanics, I've been telling you, we do all these things that are unitary during the circuit, right? Measurement step is non-unitary, but the actual quantum operations that we're doing, that we've been talking about, these rotations on the Bloch sphere, no information is entering or exiting the system. We can make a truth table using this kind of Boolean logic thing. In the computational basis, what this means is that this is 1 minus A times B, where we're using 1s and 0s for A and B there. Okay, but we have every possibility of what A and B are. We can figure out what not A and B is. Okay. Now for 2-qubit gates, we need to be able to do conditional logic. What I mean by this is that we need to be able to do something to qubit number 2 that depends upon the state of qubit number 1. But we're not going to measure qubit number 1 and then do it. We're going to allow qubit 1 to be in both states, to be in a superposition. Okay? So if you think about classical logic, we might write something like, if some condition is true, then perform a task, or else do something else. Okay, and for A NAND B, it would look like this. For quantum logic, what we're going to do is we can define what happens to the target qubit based on the control qubit. Okay, so I'm saying if control qubit is in the 1 state, do this to qubit number 2. If it's in the 0 state, do that to qubit number 2. But we do it without measuring the first one, okay? It can be in a superposition. So generically in the circuit diagram, these sorts of things look like this. You have elements in the circuit diagram that actually span across multiple qubits, across multiple lines, all right? If this open circle here means that this operation, whatever is written down here in the diagram, happens only if that control qubit is in the 0 state. This closed circle, by convention, means that it's the same thing, except it happens only if the control qubit is in the 1 state. Okay? So this would be what you would call like a controlled unitary or something, whatever U is. Okay? You're controlling it based on the state of qubit A, but this is not a measurement and then do thing. Okay? What you do is you apply this unitary here in this upper example to the subspace of the system that corresponds to qubit A being in 0. The subspace of the system that corresponds to qubit A being in 1 gets the identity operator. Okay? So if the control qubit's in a superposition, mathematically that's what this looks like. Okay? Something like this where we project onto the 0 state and we do the identity on everything. If the control qubit's in the 0 state, we project onto the 1 state and we do this unitary, whatever it is, to everything else conditioned upon that thing being in the 1 state. Okay. The granddaddy of all of these is the controlled NOT gate. Okay? So the controlled NOT gate flips the target qubit if and only if the control qubit is in the state 1. I say in quotes because the controlled qubit in general is in some superposition that we're not going to actually monkey with, okay? Right? So this is basically the description in terms of basis states, okay? And this is the symbol. So the control qubit here, we're going to do something only if it's in state 1. That's what that closed circle means, all right? And then this kind of circle down here with a line through it or a plus sign in it, this is kind of like an X gate notation in some sense, but basically it's going to flip the coefficients on the basis 0 and basis 1 states of qubit B in this case, all right? So if we want to talk about, what is the kind of truth table version of this, we can see what it does to the basis states. 0, 0 goes to 0, 0. 1, 0, well, the control qubit's in 1 here, so I flip from 0 to 1, right? Here, 0, 1, it's the control qubit's in 0, so nothing happens, right? And then here, 1, 1, I get 1, 0. And if you wanted to write that in terms of a truth table, it looks like this, okay? This, incidentally, is the truth table of the XOR, the classical XOR gate, okay? But this, it's a little bit of a dodge to make a truth table for quantum operations because we're going to allow things like phases and stuff to appear, which you can't really encode in true and false, right? But more or less, this is an accurate description of what happens to basis states. Okay. Two different versions of this. We can have the control and target actually flipped, in which case, of course, we flip the symbol here. The matrix representation of this thing, if the first qubit is in the control, and the second is the target, is this. Okay? So here, this upper portion here corresponds to what happens if the first qubit is in the 0 state and not a mucho, right? The identity. What happens if it's in the 1 state? Well, we do an X operation on the other qubit. We flip it. Okay? Likewise, if you reverse the roles of these two, it's a different matrix, right? You represent it with a different matrix. But you guys know how to do this. You would just use Kronecker products to do this. All right, so we're gonna go into this a little bit because I want you to understand what's going on here with the CNOT gate. Okay, we can write the CNOT gate in this form. We're going to do the identity if the control's in 0, do an X if the control's in 1. Okay? If you look at that X times control being in 1, we can write X for the second qubit in the X basis. Okay? So this is what the X operator looks like in the X basis. It looks a whole lot like the Z operator looks in the Z basis. Okay? It's the same thing, but it doesn't, might take you a little while to get to that point, but it is the same thing. Okay? the very last term there, right, this x2 times 1, 1, all right, we can write it in the x basis in this form. And this blue part here is kind of the only non-trivial part. This is the part that gets a minus sign. So when we introduce CNOT, if I go back here, I told you what it does in terms of these 1, 0 basis states. And what I'm arguing now is that this is actually it's a little more intuitive to figure out what's going on if you think about expressing qubit number 2 in the x basis. Okay, so that's where we're headed with this. Okay? And what happens when we do that is that all we have to do is reproduce this minus sign here. Okay? So we have to somehow or another create an operator that looks like minus sign, aka e to the I pi, times this projector, right, plus the identity for the rest of the universe. Okay? Now, this is suddenly kind of sneaky here, because if I want to produce the identity operator from some Hamiltonian, right, if this is the time evolution operator associated with some Hamiltonian, the Hamiltonian lives in the exponent. If the Hamiltonian is 0, I get an identity operator here, right? So that's a little bit of a sneaky thing. I don't necessarily have to put the identity operator in my Hamiltonian here, okay? So if I exponentiate e to the I pi times that projector plus nothing, 0 times, rest of the universe, okay? What I get is indeed that I have some kind of a non-zero coefficient on this term here with 0 on the rest of that. So when I exponentiate it, okay, which I can do by writing it this way, all right, it's a little bit more familiar. I have 1 minus z1 times 1 minus x2 here, okay? What I get is something that does essentially what we needed, the essential part of what we needed, okay? This thing is the generating Hamiltonian for the CNOT gate. What I mean by that is it's the thing that lives in the exponent, okay? And it gives us our important part here, okay? So what happens is we can decompose this thing as a product of single qubit operations and then this actually x1, x2 operation here, okay? So if you look at this thing, we have a kind of there's going to be one non-trivial cross term if I expand that, right? I'm going to get identity times identity. I'm going to get identity times x2, which is a single qubit operation, identity times z1, which is another single qubit operation, and then something like z1 times x2, okay? That is something that depends upon both the value of qubit 1 in the z basis and the value of qubit 2 in the x basis, okay? Using single qubit operations, I can turn that into doing something if the qubit 1 is something in the x basis and qubit 2 is something in the x basis, okay? So we can consider an Ising interaction, okay? If you've ever heard of the Ising model, this is spins that interact based entirely upon their orientations and in particular their orientations, their projections in the x direction. This would be an x-directed Ising model, okay? If that's the Hamiltonian, then we can use this to create the time evolution operator, right? And we end up with something that looks like this, where we have identity minus something times this kind of non-trivial operator. If I look at what happens when I apply that to a product state, an unentangled state like 0, 0, if I let it go for pi over 2, what I get is a maximally entangled state. So the controlled NOT gate can take you from a product state to a maximally entangled state. This is what we call a perfect entangler, which is going to be important when we get to our origami here, okay? One bit of notation here is that what we say is that there's a non-local part of this gate, which is this portion here that depends upon the value of both qubits simultaneously, and then a series of single qubit rotations here, okay? We can use to write this down. In fact, I could simplify this. This is going to be a Z1. Okay.
And what's the meaning of maximally entangled?
What I mean by that is just that the entanglement entropy is whatever that is, 2. That basically if I trace over one of the qubits, the other one's in a completely mixed state. That's what I would say. But any of these, if you know this language, any of these so-called Bell states for 2 qubits, that's what I mean. Okay. There's another one. Let's meet another one, the controlled Z gate. Okay, CZ gate. The notation looks like one of these two. You'll see that it treats both qubits on equal footing, so there's no difference between the control and target in this case. This notation on the left reminds you that what we're doing is we're doing a Z gate on the second qubit if the first qubit is in the 1 state. Okay? When you go through what that means, you figure out that they're actually the same. Okay? And the truth table illustrates that. All we do is take the 1-1 state to the -1-1 state in a controlled Z gate. Okay? The gate itself looks like this. So here we have a generating Hamiltonian that looks a lot like the one for controlled NOT, except that this is a Z instead of an X. Okay, or sorry, the second one is a Z instead of an X. And the matrix representation is fairly pleasing here for the first qubit. Well, actually, they're the same. Okay, all right. And so if you think about the truth table, we're starting to get into slightly dodgy territory with regard to truth tables because, well, there's a minus sign on here. This is like a phase. Okay, it's a little hard to get a phase in truth table. It's something like this. Okay, some identities. Here's an identity. You can make a controlled NOT gate where you flip the role of the target and control qubits by sandwiching it with Hadamards. Okay. Here's another one. If you want to have a controlled NOT that is controlled on the 0 state, you can make it out of a controlled NOT that's controlled on the 1 state by just flipping the qubit, the control qubit before and after. That makes sense, right? Remember the X operator takes you, flips, is a pi rotation around X. It takes the north pole to the south pole and vice versa. Okay. Controlled Z is symmetric both ways, so that one's pretty trivial. Relationship between the controlled Z gate and the controlled NOT gate is that if we put some Hadamards on here, we get a controlled NOT gate. Okay, here's another one. Swap gate, if you ever see this. Swap gate's it's a little funny to call this a gate. It's a little bit of a funny operation, particularly in the hardware platform that I work with which is trapped ions, where our qubits are physically movable. So the swap gate just kind of switches labels in some sense. We essentially take the state of qubit A and put it on qubit B and vice versa. All right? If you wanted to write down a Hamiltonian to generate that, it looks like the Heisenberg interaction, okay? XX plus YY plus ZZ, all with the same coefficient. And then we have some constant term here as well, okay? So a Heisenberg model would generate the swap gate here. The matrix representation looks like that, and here's our truth table. There is something called the I swap gate that you may encounter. All right, this comes in when you have an XX Hamiltonian, okay? What happens is we put an I on the state after we swap them for the 2 cases where we swapped the qubits and it was meaningful, okay? And we can generate that, as I mentioned, from what you would call the XY interaction here, or sorry, XX interaction, where you have X1, X2, and Y1, Y2 in the Hamiltonian with equal strength, okay? This is what our matrix representation looks like. Here's another one, square root of swap. This is now getting kind of interesting, okay? What is the square root of swap? It's like you're doing half of a swap in some sense, if we go back here to what swap was, right? Here we took the qubits one onto the other one. What if we stop halfway, okay? Well, it's the same generating Hamiltonian, we just divide by 2 up here, right? That's why we're calling it a square root of swap, okay? And when you look at what that thing does, it's again a Heisenberg model, it actually does something kind of non-trivial here, okay? This can actually create entanglement from initially unentangled states. So for instance, 0, 0 doesn't do anything, but 0, 1, which is a product state, goes to this maximally entangled state here, 0, 1 plus 1, 0. Likewise, 1, 0 goes to this maximally entangled state here. So this is another example of a kind of perfect entangling gate.
Yes.
Yep.
We mentioned in the context of trapped ions, it literally means changing them physically in space, then what does square root do to the ions in space?
Yeah, so if you wanted to create a square root of swap operation in a platform where you were doing a swap operation by physically exchanging them, I guess you would put them together and then pull them apart, but you would do it carefully in a way where you gain no information about which one went to which location.
That's impossible.
Does that make sense?
Okay.
So that, that sort of thing in principle can be done. That's not what we do, but trapped ions, they don't like getting close to each other.
Right, exactly. So you just wouldn't use this operation in your platform?
Right. We would build this out of other fundamental interactions and leave the physical qubits in their original locations. Yeah. Okay, this is the most important one for your origami. Okay, this is what I'm calling the XYZ gate. This is a name that I came up with because I think it's instructive. The inspiration for the origami came from Gavin Crooks, who calls this the canonical gate. This all comes from a paper by Brigitte Whaley, who's your Professor Whaley, who will be here on what, Friday, Thursday? Friday, right? But it's a fundamentally an XYZ interaction in a spin model is an interaction where you have a term that in the Hamiltonian multiplying x1, x2, another term of a different strength for y1, y2, and another term of a different strength for z1, z2. That's XYZ model, okay? And we will parameterize this with a real vector, dimensionless real vector t. So I have three components, txx, tyy, and tzz. What the XYZ gate does is it performs this rotation. This is my definition for what the XYZ gate does. So depending upon the value of t, you will get some evolution operator or another, okay? It treats both qubits on the same footing, which is nice. Okay, that's one of the things that I kind of like about this, but it's also, this is a sort of easy to wrap your brain around, version of a two systems interacting with each other, okay? In principle, the components of t could be any real numbers. However, there's a lot of redundancy, okay? If I add 2 to txx, I get just a minus sign, okay? If I add 2 to tyy, I get a minus sign, zz, the same thing. If I add 2 to both of them, I subtract 2, and so forth. Yeah?
So I think on the x1, x2, y1, y2, you want to commute, right? So why don't you just decompose them to three different gates instead of?
No, like for instance, the y1 here would not commute with the z1 there.
Yeah, but y1, y2 is commute with z1, z2, right? After you cancel it.
Sorry? What?
y1, y2 should be commute with z1, z2, right?
I wouldn't think so.
Because y1 anti-commute with z1, y2 anti-commute with z2. After you cancel them together,
You're going to get x's, right?
yeah, maybe I can check that.
Yeah. So I think this is non-trivial. Like you really need all three of these up in the same exponent, I think. But we can talk later. Okay. All right. So this brings us to the geometric representation of two-qubit gates, which is what this thing is. Okay. So this is your origami, and we had the block sphere as a good way of representing states of a single qubit. This is not a representation of states of a two-qubit system. This is a representation of gates or operations, okay? Time evolution operators in a two-qubit system. There is also a way to use the block sphere to represent the gates in a single qubit system. It's not all that instructive, in my opinion, but this is, I think, the best representation I've seen for two-qubit gates. So we're going to build it up, okay? And the first thing we're going to say is that two-qubit gates are said to be locally equivalent if they differ only by single qubit rotations. So if I have two operators that operate in some state space of 2 qubits, if I can turn one of them into the other one only by adding single qubit rotations before and after it, I would say that they are locally equivalent. Okay? So a good example of this would be controlled Z and CNOT, which we already showed you that those were locally equivalent, right? I can turn a controlled Z into a CNOT by doing local operations, single qubit operations before and after. Okay? Single qubit operations are the local ones. Examples in a 2-qubit space would be like this thing we called, for instance, x1, right? So in terms of the operator, this is x tensor 1, right, x1. You know, z2 would be 1 tensor z. We can also think about any rotation, right? Rotation by angle theta about the x2 direction. You can also think about, maybe I do 2 operations, one on qubit 1 and another one on qubit 2. There, I'm basically exponentiating a sum here. You can write it like this. Those are all local, okay? Doesn't matter if I do them simultaneously or not, as long as they're just acting on single qubits one at a time, it's all local. Non-trivial 2-qubit gates have to be at least partially non-local, okay? Somehow or another, we have to have some interaction that gives us conditional logic, right? We have to do something to one of the qubits dependent upon the state of the other qubit. And those terms come from cross terms in the Hamiltonian, okay? So x1, x2 by itself, if that were the evolution operator, would be local, but when I exponentiate it here, I can get something that is non-local. This is what we get for the Ising interaction, okay? So this is the paper that I'm alluding to.
One more question.
Yes?
2 locally equivalent gates, do they have the same entanglement entropy?
I don't think so. I think that there would be a way to have one of them create a certain entangled state from a given initial state, and the other one, since it effectively sees a different initial state, may not do so. Yeah. It's a guess, but I think that's. Okay. So this is the paper that introduced this by Professor Whaley here, okay? And what they did was they did something called a Cartan decomposition. Effectively what that means is that any 2-qubit gate can be replaced by a combination of 1-qubit gates and a single XYZ gate. That's the result of this fancy algebra, essentially. And this is really cool because it means that we can basically take any 2-qubit operation that we care about and draw it like this. Okay, we can replace it with this circuit. As long as we can specify what T is, and then these are my kind of single qubit operations. Algebraically, it looks something like this, okay? This is a little bit wild. I mean, I was a little bit surprised when I first learned about this. We don't need any x1, y2 cross terms or anything like that, okay? You can really just write this. This is a kind of, the Lie algebra associated with this is with each of these terms being elements is a subalgebra of the thing that kind of spans the whole space in some sense, okay? But basically, all we need is this XYZ interaction. If you have some system where you have an XYZ model and you have control over it, you can do anything, okay? Locally equivalent gates are going to share the same vector T. So I told you that we mean locally equivalent when the XYZ part of it is the same, and then the gates that act on single qubits may not be the same, okay? If the XYZ part of it is the same, that means T is the same for both of them. And we can make a state space in which this vector lives. And that's the state in which this shape lives, okay? So what I'm going to do is I'm going to show you how we make this state. I'm going to say build it, but it's going to be the other way around. We're going to start with all the possibilities. We're going to subtract everything from it that's redundant. We're going to be left with this, okay? This is a geometric shape, the interior of which contains every non-local gate, okay? So any quantum gate you can do on 2 qubits, you can represent as a point in here. So we're starting with our state space. It has 3 dimensions, or not state space, but the space that this vector lives in has these 3 dimensions to it, okay? And the first thing that we saw about this vector was that it had these periodic boundary conditions, right? So if I go along the y-axis and I get to 2, I get a wraparound boundary condition, right? What that means is that we have congruence between, T and T mod 2, essentially, right? Which in this 3-dimensional space means we have the geometry of a 3 torus, right? Think of it as a cube where we just reflect. Every time we get to this face, we pop up back here, right? Every time I get to the top face, I pop up on the bottom, vice versa, and so on and so forth. So now, we no longer need to worry about the redundancy between points that live inside this cube and points that live outside of it. We're going to take care of all of that, right? Everything we're going to say, t has to live between 0 and 2. All the entries of t have to live between 0 and 2 because those things are locally equivalent, right? I can create one and turn it into the other one by multiplying by a minus sign, for instance. Okay. What about local gates? x1, x2 on an xyz gate adds 1 to txx, and then we get a factor of minus I. y1, y2 adds 1 to y. z1, z2 would be a surprise if it didn't. Adds 1 to z. Okay? So we don't actually need this cube of side length 2. We already have found that within local gates, we only need to specify t on the interval between 0 and 1, not between 0 and 2, because we say that these are equivalent, right? So we now have a smaller cube, or smaller 3 torus, if you like, okay? Here's another one. What about this gate? This is kind of a wild one. This is sort of a rotation by pi over 2 about y1 and a rotation of pi over 2 about y2, right? And then we're going to kind of undo those on the other side, right? What this does, if you look closely, it flips x and z. The operation on this cube that flips the x-coordinate and the z-coordinate is a reflection about the x equals z plane, right? So if the points over here that correspond to a reflected point over here are locally equivalent, then I only need half of this. I don't need the whole cube anymore, right? I get to throw away half of it. I'm just keeping the part that's going to give us unique points for unique locally equivalent gates. Pardon me. So I slice it off. Okay? Let's keep going. Here's another one. All right, here what we have is y1, y2 times a similar sort of rotation, except we reverse the directions of the y2 rotations. That not only flips tx and tz, but puts a minus sign on them and adds 1. Okay? So the x-coordinate in the original non-local gate here, under the action of these local operations becomes 1 minus the z-coordinate. Okay? That is a reflection about that line, about that plane. So again, we have points down here are going to correspond to points up here if we apply local gates, which means we don't need them both, right? We want to get down to the point where applying local gates doesn't do anything to it. Okay, so now we have a little, little rooftop. Okay, let's keep going. Same thing in the x direction. Okay, if we do this, we're going to get reflections about the x equals z, or sorry, the y equals z line, y equals z plane, which is a little tough to represent in the particular perspective I chose here, but we can shave off that part of it. Okay, let's do another one. Analogous thing, we put a minus sign up here, we put these here, we're going to get that plane. Shave it off. Okay, we're starting to get somewhere. Now we have to do the same thing in z. So in the x direction and in the y direction, we've had kind of planes crossed at an x, right? The same is true here. Here we have a right pyramid, right? Okay, now we're going to slice off half the pyramid. It's out of there, okay? So now we have a, well, I don't know. This is like a skew. I'm not even sure what this thing is, okay? But basically, there's a whole face here, okay? All right? We're going to slice off with this last operation, the other diagonal direction, and now we get this thing. This is your skew tetrahedron, okay? You have, it sits like this, okay? This big face is the one that's not visible here. This is the base. These are all right angles right there, right? It's vertical. This is called the Weil chamber, which I think is a great name for a metal band. or like a metal club maybe, I don't even know what. But this is the vial chamber, and this is what you have made a model of. Yes?
Sorry, can I ask, is there a reason for choosing these local operations? Like, does it make the system very specific, or is it still general?
Absolutely. I mean, this was, you know, I'm sweeping a lot under the rug, but the key here was to figure out which sets of local operations allow you to reduce it to a single fully connected region that contains everything possible. And that was the set that they chose.
So these special choices of local operations will still keep the result general to any
That's right.
gate that decompose in that way.
That's right, yeah. So we could have, you know, slicing and dicing our cube all the ways that we did, we could have chosen any of the possible resulting vial chambers and used that. This is the one that they used in that paper, and this is the one that we have here. Okay, so let's take a look at it. Let's like meet this thing a little bit. Along the x-axis, right, that is the long axis here. Okay, so the origin is at this left-hand corner. X equals 1 is out here. The x-axis is all Ising interaction. It's all gates where the non-local part can be generated by an Ising interaction. Ising interaction is something where the Hamiltonian depends upon the product of the projection of the spins in the x direction, x1, x2. Okay? The controlled NOT gate lives halfway down there, right in the center. All right? That's also where the controlled Z gate lives. They are the same. You remember, they're locally equivalent, right? So it means they have to live at the same place in this thing. Okay? The interior of your vial chamber is generically all of the different XYZ models. Hamiltonians, those points represent evolution that's generated by Hamiltonians that have XYZ. Coefficient on XX, coefficient on YY, coefficient on ZZ. Okay? The bottom face, the base, is all XY models, right? The Z coordinate is 0 on the bottom face. So this is what you get from XX plus YY with possibly different coefficients, right? Okay? If they have the same coefficient, okay, that's this spot here, which I label spin exchange trail. I put little like hiking instructions on here, okay? That is all the XX models, is that bottom edge there. Okay? Swap lives at the apex. That's a swap gate. If you think about time evolution as increasing the exponent, right? Then what you're doing is you're basically starting at the origin and walking out as a function of time on a ray here for just the non-local part, okay? If the actual Hamiltonian you're dealing with has local and non-local terms in it, then your trajectory on this thing can be something kind of squirrely, okay? The ridge here, this is what I call, I label it Heisenberg ridge. That's Heisenberg model, okay? On the back edge there, coming up here. So if you apply Heisenberg model for T, 2T, 3T, 4T, 5T, as you go on and on and on, you'll get up here to this apex. The portions of the vial chamber that are shaded in blue contain the operations that can take at least some separable state and create a completely entangled state from it. Okay? So somehow or another, you can take something that is a product state and turn it into something that is like a Bell state if the operation is found inside the blue region here. Okay? So as part of your homework, one of the things that I ask you to do is to actually team up with each other, try to put your tetrahedra together to reproduce just the shape of the blue region and figure out what that thing looks like. And then I asked you to tell me what fraction of the total volume is occupied by that. Okay? Other notable ones, let's see here. ISWAP is on this back corner here. Quantum Fourier transform is kind of up this back edge here. This back edge is XXZ models. So the Y and Z, or the X and Y coefficients are the same, but the Z coefficient is changing as you walk up there. In your vial chamber, you even have an interior if you care to like actually make sure that you can still open the thing up. Okay? But you should be able to take any 2-qubit gate, and there will be a unique point either on the surface of or interior to this thing that corresponds to that 2-qubit gate, because that tells you what the XYZ gate is. There is one exception. The exception is that the base is reflection symmetric. So gates that are on the surface of the base, okay, actually exist in 2 points. Okay? So strictly speaking, you could imagine half the base here is like epsilon shaved off, if you want to think of it that way. Okay? I just said that they're reflection symmetric here. Okay? Most of the interesting gates actually exist right on the border between the fully entangling and the not fully entangling gates. So things like square root of swap is at these pointy parts here, right? Controlled NOT and controlled Z is at these pointy spots. I swap is back here. Square root of I swap is here. Okay? Square root of swap dagger is here. And I find that kind of interesting, but I think it kind of makes some sense when you think about what this thing does. Okay? Any questions about your origami?
Not exactly origami, but do you have an illusion for why the carbon decomposition is not this?
Oh, why it works? Why you can?
Why it exists?
Oh, why it exists? No, it's not clear to me a priori that XYZ is enough. So I found that to be a little bit surprising. Ultimately, if it's not enough, then I would have expected that you also need XY, XZ, YZ. You know, you also need all these cross terms. It'd be weird if you needed only some subset of the cross terms.
Do we know if there's sort of an equivalent for it?
If there's a what?
Equivalent for it, rather than using the XYZ?
Yeah, I would think so. I mean, you could, for instance, use local gates to transform this, right? So I could sandwich that thing in some local gates. It would create a new form for the non-local term. Yeah. Good questions. Yes.
I think you might have said this before, but what's the motivation behind like re-expressing 2-qubit gates into one single qubit gate? And can you also do this with multiple qubit gates?
Sorry, who was the last part?
Oh, can you do this with multiple qubit gates?
Oh, like more than 2?
Yeah.
I don't know of a way to do it for more than 2. We're about to start talking about gates that involve more than 2 ions, but I don't know of a way to do it. Yeah, it's a good question.
Does this shape represent a universal matrix for the gates that they can be found from?
I mean, you might say it's this. So if you want to think of that,
a generic matrix, basically.
Yeah, you want to think of that as a matrix-valued function
Yeah.
of tx, x, tyy, and tzz.
Yeah. And whichever form they take, the gates you get.
Yeah, so you can take any 2-qubit gate and decompose it into that thing sandwiched between single-qubit gates. That's sort of the result. Another way to look at it is this thing, this vector t, is a local invariant. If I perform local operations on this part here, it doesn't change t. Right? That's kind of where it comes from. It's a way of representing the local invariant. It's sort of a 3, which kind of has 3 degrees of freedom. Okay, more than 2 qubits. So an example of one gate that has more than 2 qubits involved is the Toffoli, or the controlled NOT gate. So here we have to do something only if the upper qubit is in the 1 state and the second qubit is in the 1 state. What we do is we invert the 3rd qubit in that case. So the only non-trivial parts are these last 2 terms here, where the first 2 entries are 1s. And then I flip what the second one is. Okay. This is what it looks like. That gives you an idea of what that generating Hamiltonian is. This is probably not too surprising if you go back and you look at what the generating Hamiltonian was for controlled knot. And matrix form, you just get a little whoop, whoop there at the end. Okay. Controlled swap is different from swap. Okay, here we have to swap only if that upper qubit is in the one state. And so here is the non-trivial part of that one. And the generating Hamiltonian has a Z1 times essentially a Heisenberg interaction for the second and third spins. So you're sort of taking the Hamiltonian that you use to do swap, and you're just basically conditioning it on that first qubit being in the one state. Okay, and then here we've just, looks a whole lot like the previous gate, basically. Okay. The 3-qubit Deutsch gate. So this is mainly of historical significance, or historical interest. But what this does is, for these last two basis states, it does a rotation and multiplies by I. Okay. If you want to write it as in terms of a Hamiltonian, your generating Hamiltonian is going to have a term that depends upon theta, but presumably you know what theta is, so you can choose that to be whatever you want. And the matrix representation is I think, pretty straightforward here. Okay. All right, now let's get back to talking about measurements again, because these are important. So we're going to consider two different circuits and talk about differences between measurements of these two. And this is going to get back to my earlier thing where I said, you know, it's going to be important when you're listening to Nick Chilton and Nick Hutzler later that you understand some of the nuances of measurement. Here we have a circuit. We're going to start 2 qubits in 0. I'm going to put one of them in a superposition, do a controlled knot, and then we'll measure both qubits. I'm going to compare it over here to something where we don't do anything conditional. It's all single qubit gates. So this is going to be 50-50 superposition. This is going to be 50-50 superposition. In this first circuit, at the beginning, we've got a product state. After that first Hadamard gate, it's still a product state. Okay? All we've done is put the first qubit in the X basis, in an X eigenstate. But after the controlled knot, we get an entangled state. I can't write this as a product of two single qubit states. Okay? But it's 50-50, right? Over here, we're going to have to stay in a product state the whole time. We're not doing anything that involves an interaction between the two. And so both qubits just end up in the plus X eigenstate. Here, we get a different state. This is a product state, okay, which you can tell from this, right? Also, 50-50, okay? So the average of a bunch of measurement results over here is always going to be 0. I should have said 1/2. If I measure this, if I assign +1 to 1 and -1 to 0, okay? Like +1 to spin up, -1 to spin down, they'll average to 0. I should have been more precise with that wording, okay? All right. The individual qubit outcomes, however, are correlated. Over here, we're going to get the same averaging, okay? But the individual qubit outcomes are going to be uncorrelated. So if you think back to this slide, okay, think about the difference between a measurement of ensemble average, where I'm going to measure the average value of an ensemble of identically prepared systems. If the average value is 0, I will always get 0 here. If, however, I average an ensemble of measurements, my individual measurements here will have a record of the correlations. The average is going to be the same. You're going to get the same as a result of the average, okay? But here you have access to the fluctuations. Here you notice that qubit 1 and qubit 2 are completely correlated. That's why it's very important in a quantum algorithm to be able to do single qubit measurement. You have to be able to measure the state of a single qubit deterministically. You have to be able to do that independently for many different qubits. So if your measurement fidelity is really bad, then you're actually going to lose access to the information that you need to be able to get. And it can be if you're making your qubits out of little tiny microscopic quantum mechanical things, this is kind of challenging, okay? But it's very important to be able to get a deterministic, or to be able to get a result for every single qubit when you do a single measurement of the whole system. Okay, so this brings me to talking about universal gate sets. I think actually I'm getting kind of near the end here, so we're probably going to end a little bit early. The standard universal gate set here is a Hadamard, a T-gate, and a controlled NOT gate. What this means is that there's something called the Solvay-Kitaev theorem that this basically will allow you to build any quantum circuit, okay, as long as you can implement those three things. And the choice of these three is motivated partly by some things that we haven't talked about, but that's kind of the standard gate set. I haven't proved this, but you can approximate any unitary operation using only these gates from this discrete set, okay? Alternative universal gate sets exist. For instance, you could have a Hadamard, a T-gate, and square root of swap. You can have a Hadamard and a Toffoli. Or it turns out that you can even do everything with just a Deutsch gate as long as 2 theta over pi is irrational. The reason that this has to be irrational is kind of related to the idea of imagine, let's do the single qubit equivalent of all this talk, right? Talking about doing arbitrary universal operations, okay? For the single qubit, what we would need to do to say we can do arbitrary things is to say, I want to be able to do any rotation, right? I have to be able to take a given point and go anywhere on the sphere, okay? If the only thing I have access to is a whole bunch of pi rotations, I can't get full coverage, right? But if, for instance, I have some irrational fraction of pi, then you might imagine I could do a jillion of them and get around to the right spot, right? Or think of it like a circle, a 1D example, all right? I want to be able to do an arbitrary rotation in a circle, okay? If the only ingredients I have available are discrete rotations by, say, pi over 2, I can't do an arbitrary thing. But if I have some irrational fraction of pi, then for any point on there, I can get as close as I want to that by applying, some giant number of these things. That's essentially what's at work here. Okay, and there are many other gate sets as well. All right, this brings me to the last topic, which is talking about the actual criteria we have for building a quantum computer out of physical devices. You have some physical platform and you want to know whether it's going to make a good computer. This is usually summed up in these things called the DiVincenzo criteria. And the first is that we need a scalable system with qubits. What we mean by that is that the system, I have to be able to expand the size of the system by adding more qubits, okay? This is how we gain access to that exponentially large amount of memory that the algorithm ends up using, okay? You have the Hilbert space itself obeys a tensor product structure, much like these tensor products we were talking about, right? And as long as you have to have the ability to grow that by adding additional qubits, okay? And of course, your qubits need to be well defined. You have to, be able to identify qubit number 7, right? And keep an eye on it, okay? The platform that I use is trapped ions. So this is a picture of a bunch of individual trapped ions here. We have to be able to initialize the state of our computation, which I said is typically everybody starts off in the 0 state, okay? This is one of these operations that involves some kind of an entropy exchange between the system and the environment. If you start off with some ignorance about the state of the system, at the end of the operation, you know exactly where it is. It starts off with finite entropy. You end up with 0 entropy. When I say entropy, I mean information. Okay, that's always what I mean when I say entropy. All right. So here I've written this as if we're doing measurements and then conditional rotations, as I mentioned earlier, but you could do this however you want. The third thing is good coherence. So I mentioned that we have to be able to have the energy separation between the states be really well defined. And the reason is that if these have different energies, if the 0 state and the 1 state have different energies, as a function of time, the 1 state has a e to the minus I energy times time. Right? The phase of the 1 state relative to the 0 state is linearly increasing with time. And it's given by the splitting between those energies. right? If that energy splitting jiggles around, that phase gets randomized, as I mentioned, okay? And so we lose our coherence. That's what we mean by coherence, your knowledge of the phase. There's kind of another way that you can lose coherence, which is what you might call a T1 process, which is the language from NMR. If the excited state can actually decay to the ground state spontaneously, that will also reduce coherence, okay? So you need these states to be long-lived, have a really well-defined energy separation between them. And what that means in terms of our circuit diagram is that these lines can get really, really long. T can get really, really large, right? Time can get really, really large. And we still have accurate information about what those states are. We need a universal gate set. I just gave you some examples of universal gate sets, okay? And the 2-qubit ones in particular are kind of tricky. But this is an example of kind of the meat and potatoes of Shor's algorithm here, okay? And then last, we need to do individual qubit readout. And for that, we have to be able to get an answer for each qubit in a single shot, okay? So this shows you fluorescence from atomic ions, where the fluorescence indicates what the measurement result is. That's how we do it with atomic ions. And you know, that often will just be necessary for a subset of the qubits. Okay. So that is actually my last slide. So I'm happy to continue on with questions, but this leaves us with maybe an extra long break for lunch or whatever. Yeah. Questions?